everybody. Today we'll talk about do's and don'ts in structural steel framing and connection design, which is basically tips in steel framing and in connection design that could result in a great economy, simplicity during construction, and elimination of many RFIs. So best design is the one that provides the steel fabricator with options and flexibility. Now, the steel fabricators, which are also typically the erectors in many cases, they need some flexibility to in the connection design, also if they are involved from the beginning in the for example the design build project, they can provide great suggestions that could save on steel, that could save on labor, and would result also in simplicity in the construction, and also avoid many RFIs, because RFIs typically come from them for structural steel. So it's very important to have them involved and give them options and flexibility in the connection design in particular. Now, for every project or detail, there could be several good solutions. I mean, there's no one good solution. So there could be several good solutions. And of course, with coordination with the, of course, steel fabricators and the design team, we could come up with a most efficient solution for the structure that we are designing. And also best solutions depends on the local construction practices and contractor preferences. So whether your project is in the East Coast or in the West Coast, or whether your project is in the US or outside the US, like many companies do such work, international work, we have to know what are the best practices and what are the contractors' preferences for that region that may result in, again, ease of construction, economy, being on a schedule to avoid, of course, RFI as much as possible, and would result eventually in a successful project. Now, constructability is one of the main issues. So constructability equals economy. So if the construction process, if the erection of steel in particular is simple and easy, that results in economy. That economy is translated in saving in material, having less pieces of steel in the project, and also it depends on the time schedule, whether we are on time or ahead of time or over time in the construction schedule or the erection, in particular in this case for structural steel. And of course, if that would affect, of course, the next phase, or if the steel is done earlier, of course, the next phase of the construction it could start earlier and finish also ahead of schedule. The principles of constructability are simplicity, which equals economy. Least weight does not equal least cost. So as designers, and like we learned in school, okay, to select the lightest shape, for example, okay, this is important, but that's not everything. At the end of the day, yes, the steel is based on the weight, but not the weight only. There's also the labor. So it depends on how simple the erection process, how simple are the connections. And connections, of course, is the main item that could result on great cost if things are not done properly, as we will see today. Fewer pieces, greater economy. This, of course, has an effect on the labor. okay? And also on the material. So if we have fewer pieces, this will result in greater economy. Efficient connection design equals reduced cost. So this is a big item. So for every element in the structure, we have connections. At least one connection, sometimes a minimum of two connections, of course, if it's a beam, for example. So efficient connection design is very important. There's a lot of labor into that. There's a lot of material into that. If we are talking about plates, stiffeners, of course, weld, which is expensive. We're talking about bolting. If we're talking about, if it's slip critical surface preparation, if we're talking about pre-tensioning. So all that is labor and is related to the connection. So it's very important to have efficient connection design because this will result in reduced cost. The first thing, the first important thing that's related to connection design is beam reactions. So show beam reactions on the drawing. So which is becoming like a typical practice, you know, these days, based on what I see. Now, there's, of course, before, connections used to be designed for like full capacity of the beam shear or for a percentage of the full capacity, say 40%, 50% of the beam shear, which is not needed in many cases. So if we show the reactions on the drawings, which is easy to get from computer softwares these days, we can have significant savings in the connection design. So instead of having 6 bolts that go along the beam depth, we may have 2 bolts that are enough. And instead of having, you know, 18-inch weld, maybe, you know, 9-inch, 8-inch weld should be enough. So that depends on the reactions. So if we show the reactions, we allow the connection designers to design for that force. Excessive conservatism in connection design does not enhance safety. Okay, so of course, if we provide connections for the full depth of the members, you know, this may actually change the behavior of the connection, you know, for like simple to maybe semi-rigid connection sometimes, which is something that's not accounted for in the design. So it's important, and the solution for this, it's important to show the reactions, and the solution for this is just to show them on the drawings and have the design pair those forces. There's no point to design for the full capacity of, for example, a W16 by 31, which could be 80 kips, if we need only 25 kips. There's no point for that. It's a lot of waste of material and labor. Do not design connections for full shear strength of the member. We just talked about that. Do not have notes on the drawings such as connections shall be designed to support the full shear strength of the member. Okay, these notes used to be on the drawings in the past. Okay, if you look at old drawings, you could be, not really old also, you should see something like this. And I have seen this early on in my career as notes on the drawings, and also even a percentage of that. And do not show notes such as connections shall be designed to support reactions occurring from uniform loads equal to 150% of uniform load capacity of beams from table 3-6 in the AISC steel construction manual. Now, this is a famous table that gives the maximum uniform load for every shape, W shape. Okay, so many engineers, refer to that, and they used to have such notes on the drawings. I mean, this is excessively conservative and could result also in insufficient strength in some cases, like this case. So here, for example, if we have a beam like this, okay, we have the uniformly distributed load for this beam like many other beams. 2.2 kip per linear foot, for example. But if we have such note, we may ignore a beam that is supporting a concentrated load like this, 200 kips, at a distance 2 feet from the right support. So look at the reactions. The left support has 54 kips. The right support had 234 kips. So this may result in an inefficient design, of course, inefficient connection design, and also may result in a failure if this is not done properly. But if this beam is on the plans and we show at that end we have a 234 kips, then the connection designers will design for that force. Okay, moments and axial forces provide, this is similar to reaction. So here, same thing, provide moments and axial forces. Moments, they're used for moment connection design. So instead of designing for the full member capacity in moment, okay, which is, you know, still done until today by many, many engineers, okay, we can just design for the moment. Okay, that frame or that connection in a moment frame has a force on it, a moment on it. So provide that moment and let them design for that. If it's a bolted connection, it will result in much less bolts. If it's a welded connection, it will result also in less weld sizes and lengths. And also the plates, if we're using plates, the top and the bottom of the beam for the moment connections, we will have thinner plates than, you know, like than thicker plates that are used for the full moment strength of the members. Axial loads. They are used for, you know, the design of braces in braced frames, truss members, hangers, drag struts. So for the connections of these members, it provide the forces. It's, you know, like braced frame, just show the force. Show the force on the frame elevation that is shown in your drawings. So they have an idea of what force they need to design it for. Of course, that depends if the connection is, of course, if the frame is a seismic frame with R equal 3 or less, or R greater than 3, we will talk about that. Of course, it depends. But regardless, even if it's a seismic frame or not, show the forces on the braced frames. Trusses, it's the same thing. Trusses have many members. So if we show forces, this would result on a lot of saving in the connection design for the trusses. Same thing for the hangers and for the drag struts. The reaction directions. So it depends whether we have like a cyclic loading on the members, like case of earthquake or wind, or whether we have gravity loads on the wind. So show the reactions of your forces on the drawings to allow the designers, to connection designers, to understand how the moment is applied, where's tension, where's compression, and let them design, you know, for that. So there is no need to design for cyclic moment if it's just a gravity connection. So maybe in one side of the connection will be, you know, heavier than, you know, the other side where it's not needed. Follow building code requirements for connection design. So gravity connections and non-seismic are designed per AISC 360. Seismic connections are designed per AISC 341. So it's very important to specify that, because if we are using seismic connections, there are more requirements for the connection design. It depends, of course, on the system as shown in AISC 341. Now, gravity connections and non-seismic connections, meaning with a system with a response modification factor that's equal to 3, R equals to 3 or less, then we need to use only AISC 360. So many of the requirements of AISC 341 are not needed. So it's important to specify that, and we should not mandate connection design beyond the requirements for the connection design. It could be a building in a high seismic zone. okay, with a response modification factor equals to 3. If it's a small building that is sufficient for to use a response modification factor R equals to 3, there is no need to use AISC 341, which has more requirements for the connection design. Use bearing bolt strength where permitted by building code. Do not. So this is very important, and I have been dealing with this a lot recently in multiple projects, where I see a lot of use of a lot of slip critical connections or pre-tensioned connections where it's not needed. Use bolt bearing strength where it's permitted by the code, and we will talk about where this is used and where we need to use pre-tensioning or slip critical connections. So do not use notes such as all bolted connections shall be designed as slip critical connections. There is no need for that. And slip critical connections require, of course, pre-tensioning. They require also surface preparation, for the coefficient, for the slip friction coefficient that's in the code, and of course, it requires a lot more labor. So it's very important to use bolt bearing where it's possible. Okay, it's easier for fabrication. It's also cheaper in terms of surface prep and erections. Do not use notes on the drawing such as connections within 3 feet or 1 meter of the columns. Show where that connection is. I mean, just specify the connection, show the connections on the drawings that need to be designed. Do not use such notes like this. Connections directly supporting columns. Okay, we have in a building, we have, of course, fewer number of columns, but we have a lot of beams, right? If you think of a floor plan, how many columns do we have? And then how many beams do we have? So we have a lot of beams compared to columns. So, and we have beams framing into girders. So avoid using notes like this. Bracing connections, okay? Take each connection and deal with it, okay? If you're not designing that, of course, the connection designers or the fabricators are designing that. So all you need to do is just show them the forces, show them a typical detail, and they will design it, okay? Connections to plate girders. Okay, so this is a connection to plate girders, of course, should be done by the engineer who is designing the the whole building, not the steel fabricator. Okay, the plate girders, of course, are composed, as from at least 3 plates welded together, forming an I shape. So that need to be designed completely by the engineer, not by the steel fabricator, and of course the connections to it. So use bolt bearing strength for all when standard or short slotted holes are used, and of course when the load is perpendicular to the slot. Okay, fabricators prefer the use of short slotted holes to allow them use some tolerances. So give them the flexibility of that and use bolt bearing strength for the bolted connections. Do not use notes on the drawing such as stair connections, cantilever connections, hanger connections, connections supporting 50 kips, or if it's in metric 222 kilonewton or more. So do not specify these. As I said, deal with each connection, whether you design it fully or in some cases you have a typical detail with reactions, and then it should be designed properly for that force. So bolt bearing connections are also used in seismic systems with a response modification factor greater than 3. So consider that. So we don't have to use slip critical connections in seismic systems with the response modification factor more than 3, like ductile seismic systems. So even with those, we can use bolt bearing. Pre-tensioned bolts or welds shall be used for the following connections. Okay, so pre-tensioning need not to be used everywhere. or use pretensioning, for all the connections and things like that. So there are some locations where we need to use pretensioning, such as column splices in multi-story structures over 120 feet height, connections of all beams and girders to columns, and any other beams and girders that brace the columns in structures over 120 feet, which is basically in height, which is basically a high rise. So the definition of a high rise is for a building that's more than 120 feet, which is based on the firefighters, requirements for buildings. So that's pretensioning, but pretensioning does not mean it's slip critical. So we can use, or sometimes we have to use pretensioning with bolt bearing type connections, and of course that depends on the type of the bolts that you're using, such as F1852 bolts, F2280 bolts. Those are like twist off bolts. They're called like twist off bolts, which is basically a way of pretensioning, but these are not used for slip critical. So those are used for bearing type connections. So we don't have to use slip critical if we use pretensioning. This is very important because there's a misconception about that. Okay, if it's pretensioning, it's slip critical, or slip critical, of course, has to be pretensioning. And structures carrying cranes over 5-ton capacity, roof truss splices, truss connections to columns, knee braces, and crane supports. So for those, we have to use pretension bolts. Connections in machinery supports and other loads that produce impact or load reversals. So for those, we have to use pretensioning. So the use of single angle, single plate connections. Do not specify on the drawings requirements like avoid one-sided connection if possible, and do not use for beams deeper than 18 inches. Okay, so like one of the popular connection types is double angle connections. Okay, but in many cases, this is not needed. Depending on the reactions that we have on the drawing, we could use a single angle connection, and it would give us the capacity that we need. And many other cases, we could use a single plate, a shear tab connection, and it should satisfy, the load that we have. Okay, so this is very important. So consider using, single sided connections, not double-sided connections whenever that is possible. Do not specify on the drawings. All bolts shall be 3/4 of an inch diameter. All holes shall be 13 over 16th of an inch. Now, this is related to the flexibility that we need to give to the steel fabricators. Okay, so this is something also that I see a lot, and I saw it also on, many drawings, and I was instructed also as a young engineer back then to show this and use notes like this, like many other notes, but do not limit the fabricators to a single size of bolts. Give them the flexibility to use whatever they want, of course, with the coordination or with the engineer. Okay. Do not specify on the drawings. Okay, so this is so all fabricators determine the bolt size and type when connection design is delegated to the fabricator. So when we delegate the connection design, okay, people do that either with the reactions, or before they used to do that even with a table, for example, on the general note sheet or on the steel detail sheet. So based on these reactions, they determine the size and the number of bolts required. So give them the flexibility to do that and do not limit them. So fabricators prefer short slotted holes to accommodate tolerances and to facilitate erection. We talked about that. So let them have say on that. It's allowed to use short-slotted holes with snug, tight bolts for most types of shear connections. There is no issue with that. If they use short-slotted holes, well, of course, with the load perpendicular to the longer side of the slotted hole, so we can use snug, tight connections, which is the preferred type for erection, and also it's the cheaper type. So delegate connection design to fabricators. So according to the AISC Manual of Standard Practice, AISC 303 2016, the owners designated representative for design shall indicate one of the following options for each connection. One, the complete connection design shall be shown on the structural drawings. So that in that case, the structural engineer who's designing the building should design all the connections and show them on the structural drawings, which is a practice that's followed, for example, in California. Two, in the structural design drawings or specifications, the connections shall be designated to be selected or completed by an experienced steel detailer. Okay, so this is delegating the work to experienced steel detailer. Three, in the structural design drawings or specifications, the connections shall be designated to be designed by licensed professional engineer for the fabricator. So the third one is typically the case. So the fabricators, they have licensed professional, the good fabricators, they have licensed professional engineers who are working on the connection design. And of course, they are licensed and they stamp the connection design calculations and send them to the structural engineers for review. Now, in the case of 2 or 3, where the connection design is delegated, okay, the following shall be provided in the design drawings. Any restrictions on the type of connections. If there's any restriction by the structural engineer of structural engineer of record, should be shown. All data concerning the loads, shear, moments, axial forces, transfer forces that are needed for the connection design. Okay, we talked about that. All the loads should be given, whether the data provided are service loads or factored loads. This is very important. So you show reactions, you give forces, moments, axial force, in trusses, in braced frames. You need to indicate whether this is service load or factored load. Okay, and then whether to use LRFD or ASD design philosophies in the design. So that should be indicated by the structural engineer of record. Okay. Specify code for non-seismic. R equals 3 connections. Example AISC 360. So if the seismic system with a response modification factor, or let's say if the lateral system is with a response modification factor R equals 3, then we need to use AISC 360. We do not need to use AISC 341, the seismic provisions, okay? So for seismic connections, specify the code to be used like AISC 341, okay? So if the response modification factor R is more than 3, 3.25, 3.5, 5, 8, depend on the system that you are using, then we need to use AISC 341 and you need to specify that. Framing to columns. So frame girders to column flanges and frame beams to column webs. Okay, girders typically support columns, right? So they have higher reactions. So the result is bigger beams. Okay, so bigger beams may be, this means that, could be deeper or the flange could be wider. So we frame those to the flange, because the flange, of course, we have more space, of course, in the flange to have a connection, as we can see. Of course, that depends on the size of the column, and we will talk about that. And also the beams typically support less loads than the girders. So the beam will be smaller, the flange width would be smaller, so it can fit actually between the column flanges, as you can see. So this way we will have we can avoid, of course, coping of the beams and having stiffeners for reinforcement or anything like that. So this is important. Size columns to eliminate the need for stiffeners. Okay, so columns in general, if we look at a steel package, columns in general would have probably the least cost. Okay, as I said before, consider a floor, see how many columns you have, how many beams you have, and then the beams will have many connections, of course. So when we are designing the connections, there are limit states that we need to check, of course, in the column flange, in the column web, whether we need the continuity plates or not, whether we are framing to the flange of the column or framing to the web of the column. So we can eliminate some of the issues that may arise, such as having reinforcement requirements, using plates or stiffeners and things like that, or maybe coping. We can just increase the size of the column, although that's not needed for the column load, but this would simplify the connection significantly. Okay, so as you can see here, for example, the connection to the flange, you can see the plates, the bolts, and the connection to the web. So everything is okay. It seems to be okay there. And in the middle, you can see difficult or impossible to install. So where we have to, cut or cope the, the beams and framing into the web. And of course, once we provide coping, then there are more limit states that we need to check at the end of the beam. And as you can see also on number 2, where we have to use, if we are not doing any coping, then we are using an extended plate. Okay, and look how many bolts we are using in the extended plate. So we're using 3. We're using 3 columns of bolts with 4 rows. And of course, in this case, we have to design for the moment due to the larger eccentricity in the connection, and of course, distribute the load properly between the bolts and the welds, which also from a design standpoint would require an effort from the structural engineer or even the connection designer who's designing this. So this could be solved to a simpler connection by increasing the column size. Make opposing beams the same depth. Okay, so here you can see we have 2 different beam depths of framing into the column. And we are using continuity plates at the top between the flanges and an inclined plate at the bottom between the flanges. Okay, so whenever we have anything skewed in a beam framing or in a column orientation or in stiffness of plates, that requires more work and its efficiency is less and would require more checks in the design. So in a case like this, okay, consider using the same beam depth on both sides of the column. Okay, use deepest practical column. Okay, again, this is for connection design. So typically the column sizes we use for like typical buildings. Okay, we're not talking about like high-rise buildings where, maybe composite columns are used or maybe built-up columns are used. So just, for 80% of the buildings that we design every day, the typical column sizes range from W8 to W14. Okay, of course, W8 is not recommended because, you can see the depth of the section is small, and sometimes it's hard to fit in a connection into a W8 section. So our recommendation typically is to use W10 or more. Okay, W10 or more. So as you can see, if it's W10, there's more room to fit in the connection. If it's W12, it's even more. And if it's W14, it's even more and more. So use the deepest practical column possible, and also depending on the design of the column, you can also use, maybe a W14 with a less weight than a W8. Say W14 by 22 versus W8 by 31 or W8 by 40. Okay, even the weight will be less, but this will allow a better erection and simpler connections in the project. Orient columns to minimize skewed connections. Okay, so you can see that if we have a skewed column, we have on the left 3 skewed connections and 1 square connection, versus on the right we have 3 square connections and 1 skewed connection. As I said, we need to avoid anything that is skewed on the members or in the connections, because this would require more work. Okay, orient columns in braced frames square. So if we have a braced frame like this at the top, so you can see the columns, how the columns are oriented. This would result in complicated connections to the web and to the flange from each side, versus if we have connections to the column flanges. Okay, it's preferred to the flanges, of course, but if it has to be on the web, of course, we can do that. And if it's square, it still be much simpler than a skewed column. This is an example of a connection that is braced to the flange of a column. So it's a simple connection. It's an economical connection. As we can see, we have the members, we have the gusset plates, we have the angles without any stiffness or additional plates for reinforcing. Versus if we have framing to the web or to a skewed connection. So you can see on the left, we have a beam framing into the column flange. So you can see 1 row of bolts, simple, a clean connection. Okay, in the middle, we have a beam framing into a skewed column and to its flange. So look at it's the same beam, the same column. So with the same force. So we here, as you can see, we end up with more bolts with a longer connection, which we may need to, of course, we have to design the connection for an additional moment due to the eccentricity. And in the third case, and of course, in the middle one, we are using fillet welds. In the third one, of course, due to the large eccentricity, in this case, for example, 17 inches, we have a lot of bolts. We have 4 times the bolts that were needed on the connection to the left, sorry. And we are using CJP weld, which is expensive, instead of, for example, fillet weld. Okay, so these are the consequences of using skewed columns and maybe framing into the web versus framing into the flange. Of course, this is whenever possible. Do not frame more than 1 beam on one side of the columns. So on the drawings, we see things like that, right? So we have a column, we have another skewed, we have a beam, and then we have another skewed beam that's framing into the column flange. Now, of course, on the drawings, this may be shown as a line, as we can see. It's just a line. But that line has actually geometric properties. Of course, today with like the use of Revit and 3D modeling, we could see that. We could see that if we, of course, pay attention to it. But this, of course, in reality, will be something like this. So 2 lines are coming to the flange of the column, so there will be a conflict between the flanges, and we have to, of course, cope the flange to allow framing it. And then we would require web reinforcing, of course, if required, depending on the forces that we have. So that is by adding an angle from one side or maybe from both sides. This angle would require welds, for reinforcing, and that's more material, more labor, and even more engineering work, okay, for the design. Reconfigure framing for steeply skewed connection. So if you have like in the case on the left, so we have steep skewed connection. So instead of doing that, reconfigure the framing, see what else can be done. So we have a skewed beam, and then we have another straight beam from the other side. So what we can do is maybe have another beam between them, cross beam between them, and then have the beam framing into the straight beam between the skewed one and the straight one, as you can see. So we can add a header beam that takes that beam, and this way we will end up with a simpler connection. Configure framing to minimize skewed connections. Again, skewed connection, avoiding skewed connections, okay? So here, as you can see on the left, okay, we have 2 straight beams and 3 straight columns, right? So we can have the framing like this, okay? It's not wrong, but it's more expensive, okay? This will result on many skewed connections, as you can see. Look at the beams and the girders, how they meet at what angle. So this results in skewed connections versus the one on it's the same thing, the one on the right, okay? So we changed the orientation of the beams, the interior beams, and we ended up with much less skewed connections, okay? I mean, it depends on the shape of the building. Sometimes we have to have some skewed connection, but the thing here is how to minimize the number of skewed connections. Favor using circular column sections over square rectangular skewed connection. So if we are using a circular section, then every connection will be square, right? Every connection will be square. We don't have to use bent plates. We don't have to use stiffeners. We don't have to use like CJP weld or anything like that. Versus if we use a square HSS or rectangular HSS, as you can see, it's the same connection. We have 2 skewed connections in this case. Okay, so we can use a circular column to avoid all the skewed connections. Connection interference for beams that are slightly offset, from the column. So we have to be careful about that. So again, when we have lines like on the right, so it's shown as a line, may not show an issue, but in reality, we will have connection interference. So we have this column that's coming from the top has a connection, and then the beam that's coming from the top has a connection, and then this beam that's coming from the left has another connection. So we will have connection interference here. So we need to avoid that. Increase beam depth to avoid web reinforcement. So you can see multiple cases here where in the case on the far left, we have a W14 beam. It's required, like the top steel elevation requires this, okay? So the W14 is at a higher elevation than the girder, than the supporting beam, right? So if we are using a W14 beam, then we end up with with a cope, and then we end up with 2 bolts and of course a smaller, shallower web, which would require a reinforcing plate, as you can see. So instead of the W14, we can use a W18, which will eliminate the reinforcing and also will give me more room for more bolts and a stronger connection that would accommodate the load, okay? So you can see on the um, right, also, even when we have like the beams are at the same level, but we have, of course, skewed connection. This would require coping, and as a result, this would require reinforcing. Those angles along the cope are required. So we could use deeper beams to avoid that. Columns must have sufficient wide flanges to accommodate beam connections. Okay, so we prefer to frame to column flanges. So the column flange should have adequate width to accommodate the connection. So we talked about the use of like larger column sizes to accommodate the connection. This is also related to it. It's not like, for example, going from W8 to W10, but also selecting a column size. Okay, pay attention to BF. That's the width of the W section. Okay, that's where the connection will be. Choose a section that can accommodate the connection. Size members to have sufficient strength at net section, right? So when we design members, for bending, for shear, we design them for whatever bending moments we have, whatever shear forces we have, correct? Now, in the connection design, of course, we will have holes, we may have coping, okay? So it's important to pay attention to this from the beginning to avoid any issues later related to like reinforcing and coping and things like that. So a rule of thumb is the maximum recommended stress ratio at the gross section, the required strength over the usable strength, maximum of 0.75. So this is a rule of thumb. If you have such a ratio, utilization ratio, then you may not have issues at the net section strength when designing the connections. Communicate and coordinate. Discuss with the architect if his design is creating structural inefficiencies. Okay, so you are the engineer, you are doing the design, and if there are any issues that that the structure will be inefficient in certain locations of the building, discuss that with the architect early on before getting into shop drawings and things, or even like erection or fabrication, things like that. Failure to proactively communicate may put you in the corner. So somebody would tell you, you should have told me this. I could have done something else. I'm particularly talking about architect in this case, or maybe the mechanical engineer, the MEP, if they are running ducts that would penetrate beams and things like that. So we have to be careful about this, and we'll talk about that. This is also related to communication and coordination. So somebody may tell you, well, you should have told me this earlier. I should have changed my design. So maybe changing their design would be simpler than changing your design. Okay, so that's why it's important. Ask your client in writing for information you need and give dates to submit. Okay, that's alphabetical. That's very important, and in every stage of the project. Anticipate what other consultants will be doing in order to avoid coordination problems and interferences during construction, right? So MEP, architect, that's, I think, what's most important for the structural engineer, to coordinate with them everything to avoid any problems during construction, such as this one. So you have a big opening at the end of the beam to run a duct for a mechanical engineer. Okay, look, this is a deep beam. Most of the web is gone. So this is due to lack of coordination. So an opening like this, if it works, it would require a lot of reinforcement around that opening from the 4 sides. plates, welds, you name it. Oh, and if it works, because this is really a large opening for such a deep beam. So the mechanical engineer could have done something else. They could have rerouted this duct somewhere else. Okay, so that's why coordination is important. Do not delegate design of reinforcing around beam webs to fabricators, okay, such as fabricator to reinforce webs at openings where required, develop shear in beam, okay? This is not the responsibility of the fabricator. You design the beam as a structural engineer, and if you have something like this, then you have to design the reinforcing. You have the forces, even if you provide the forces, of course, the reactions and everything to the fabricator, you need to do that. Provide sufficient information on drawings to minimize uncertainty among bidders. So, and this is according to the Code of Standard Practice for Steel Buildings and Bridges, AISC 303. Permanent bracing column stiffeners, column web doubler plates, bearing stiffeners in beams and girders, web reinforcement openings for other trades, and other special details where required shall be shown in sufficient detail in the structural design drawing so that the quantity, detailing, and fabrication requirements for those items can be readily understood. And this, of course, will avoid issues of asking for additional services and things like that. So have everything from the beginning, show all the information. Bracing, column stiffeners, doubler plates, web reinforcing, opening, etc. Show everything so during bidding they can see all that, all what's required. Do not delegate design of plate girders, right? We talked about this at the beginning briefly. Okay, plate girders, as you can see, composed of like 3 plates, for example, in this case, and they are with weld, okay, fillet weld between the different plates. So the design of the weld is part of the design of a plate girder, right? That's how we learned in school. When you design this, okay, you design the plates. They're mostly what would control the design in plate girders is shear yielding and shear buckling, right? Whether we need intermediate stiffeners or not, or bearing stiffeners or not, and also the weld between the flanges and the web. That's part of the design of a plate girder. So do not delegate that design. And of course, use fillet weld size for the required strength. It's easier, it's cheaper. And in cases like this, always, not only cases like this, the CJP would be very, very expensive. Think about connections. Connections will be detailed when connection design is delegated to fabricator. So if you have 2 plate girders like this, okay, think about how the connections will be done in a case like that. Okay, so and always think about connections, and that's meaning how the members are put together. So you are designing steel building, okay? While you are designing or sketching or viewing drawings, after maybe receiving framing plan from the CAD designers, think about how the connections or how these members are put together. What type of connections can this be done or it cannot? And this is an example. For example, when you have a double plate girders. Configure HSS framing to simplify connections. So do not cope HSS sections. For example, in the first case, this is not preferred. Okay, cutting HSS sections affect like it will release some residual stresses, in the member as a closed shape. So this is not a preferred option. Use an end plate with shims if required. That's okay. Okay, number 2. And then number 3, use a single plate connection to the HSS column whenever that is possible. Okay, it's very simple. Single shear tab, bolted to the white flange and welded to the wall of the HSS. And then number 4, using a through plate. Okay, using a through plate actually would using a through plate is allowed. So it's one type of the connections, but it's more work, right? I mean, cutting the HSS member and then having a longer plates and providing welds from both sides of the columns. So it's a lot of work, okay? It's a type of connection that's used, but we can avoid that by using a single plate connection. Welding tips to enhance constructability. Strive to downhand or vertical welds, right? Avoid specifying all around welds unless they are needed, okay? And this is something that can be done easily by, okay, you know, having that circle in the weld symbol all around. You don't need that, okay? You don't need that. You can specify the weld maybe in 2 lines, maybe in 1 line, maybe in 3 lines. It doesn't have to be all around. Avoid specifying arbitrary CJP weld moment connections. Okay, as we said at the beginning, design the moment connections, provide the forces. Okay, provide the forces provide the moments at the moment connection. Okay, for these forces, you can design with smaller plates, with fillet welds, maybe with less number of bolts or smaller size of bolts, and avoid using CJP. I know this is simple, typical detail by preparing the flanges at a certain angle and then show CJP. It doesn't need to be checked from an engineering standpoint. It doesn't need to be checked, but that's not the best solution if we think about work, if we think about labor, erection, and cost. Favor fillet welds over groove welds. Whenever that is possible, use fillet welds. Choose efficient diagonal brace. So in braced frames, okay? So the layout of the braces is important. Single angles, good for small loads. Double angles, efficient connection, double shear bolts. If we have high shear that need to be transferred, so we can use double shear, so we can use double angle connections. HSS braces, highest brace strength per pound of steel. These are very efficient members as braces, square or rectangular. So those are used in this. Of course, there are some issues, of course, with the local buckling and rupture. It depends on the system that you're using, whether it's a seismic system or not, but still they are efficient systems, efficient members and lateral systems and braced frames. W shapes, they're good for high axial loads, but the result is more difficult connections. And those typically are used in high-rise buildings with braced frames. But again, the connections are difficult, and we can see that here. So single angle or double angle connection, brace connection, you can see it's simple. So we have the angles bolted to the gusset plate. That's simple. If we have an HSS brace, typically the brace is slotted, inserted into the gusset plate and welded by fillet welds. And then if we have a W shape, as you can see, we need angles that connect the flanges of the brace, the white flange brace, to the gusset plate. And also we would need also, in many cases, we would need also a splice plate between the web and the gusset plate, and sometimes 2, not one from each side. It depends on the connection that you are designing. Choose slopes of diagonal brace at an angle of 35 to 55 degrees. Okay, so typically the brace will be efficient between 35 and 55. If the angle is small, the brace will not be that efficient. So what could be done basically is just having 2 braces that brace to the middle of the braced frame beam, as we can see on the right. So this way we increase the angle of the braced frame, and we will end up with a more efficient brace. Okay. Also, the connections. It's not only the brace and the efficiency of the brace. Look at the connections. So if we have a brace at a smaller angle, look at the gusset plate that we need. Okay. So of course, working with like work points for the braces with the columns and the beams and the brace below, as we can see on the work point on the left. Okay, so we end up with a large gusset plate versus if the angle is typically between 35 and 55, ideally 45, right? Ideally 45, we will have a much smaller gusset plate. Okay, verify that the framing can be installed. Okay, so again, on the drawings, we show like the figure on the left. Okay, we have like we're showing the braced frame by lines, like stick model, right? And then when we look at reality and the width and the dimensions of these members, so we can see how these members can be put together. Okay, how can be erected and how can be connected. Versus so the middle one is ideal, and then look at the third one. Okay, the one on the right. So framing and geometry present installation challenges. Okay, so you can see how the brace is shown here. Okay, without consideration to, for example, work point and things like that. So the gusset plates are they are shown in their locations and their right locations, but the brace does not extend, is not fully connected with the gusset plate. So in a case like this, we have to enlarge the gusset plate to accommodate the brace, and of course this will create, of course, more cost and difficulty, and of course additional checks, because now the weld points may not align. This would require additional checks from the engineer. Configure framing to minimize the number of beams. Okay, so here we have, like, say we have one bay, it's 20 by 40. Okay, so as you can see here, the beams are in the short directions, the girder in the long direction. Okay, we don't do that usually, but you may see that. So typically we have the girders in the short directions because they support more load, and the beams in the long direction. So you can see the result here is fewer beams, fewer connections, and fewer crane picks during the erection. Okay, so it's the same bay, but look at the difference in the beam numbers, connection numbers, and also on the erection. Maximize slab span to minimize the number of beams. Okay, so here we have a 30 feet by 30 feet bay. Okay, we decided the spacing to be 6 feet between the beams with a 5-inch slab, concrete slab. Okay, so that's a metal deck plus concrete. So we could use a 6.5-inch slab instead of 5-inch, increase, and this will give us, of course, longer span between the beams, because how do we set the spacing between the beams? Based on the span of the metal deck with the concrete, right? So we can have a thicker slab with a much less number of beams, as you can see. So here you can see a number of benefits: fewer pieces, less steel weight, fewer connections, fewer crane picks, more tributary area per beam, which is greater, which will give us greater live load reduction on the beam, more mass per beam, that's less vibration, more mass. Of course, this is a building vibration. So here we have the slabs are spaced at 10 feet. I'm sorry, the beams are spaced at 10 feet. So they're supporting larger tributary area from the slab, and the slab is also 6.5 inches thicker. So this actually gives us more mass. It helps more in eliminating the vibration problem. Okay, this is of course a thicker slab, so you have a greater composite beam nominal strength also. Okay. For seismic design, use R equals 3 systems when possible. So when we are looking at lateral systems, if we can, whenever we can use response modification factor, lateral system with a response modification factor equals to 3 or less, that will eliminate the use of the seismic provisions AISC 341. And for the connections, for the member design, there are a lot of requirements for each system, and the seismic specifications the AISC 341. So whenever that's possible, sometimes it's not possible. It depends on, of course, the seismic design category you are in. It depends on the height of the system. Sometimes this is not possible. So whenever that's possible, we use it. Ordinary, for example, ordinary steel breast frames, they have 3.25 R. Okay, so you see the difference is not much between R equals 3 and R 3.25, because we have, for example, special moment frame has R equals 8. Special concentric breast frame R equals 6. Okay, so the difference between 3.25 and 3 is not much, but the requirements for once we are more than 3 are a lot. And we have to use now, in addition to AISC 360, we have to use AISC 341 and satisfy all the requirements for the system, for the seismic system. Once R is more than 3, it's a seismic system, and we have to use the seismic. Orient columns in moment frames for strong axis. So as you can see here, when the columns at the top figure, when the columns are all oriented in the strong axis, so we have each moment connection takes about 20%. So that's so the load can be distributed easily. We will end up with reasonable moment connections, not heavy. In the middle figure, so the 3 inside columns are oriented in the strong direction, so they are taking 26% each. The edge columns are oriented in the weak direction. They are taking 11% each, right? Because it's the weak axis. So instead of doing that, okay, instead of having a moment connection to the web, which is complicated, then we can eliminate these moment connections at the edges and just have the moment frame in 2 bays, as you can see, and each column will take 33.3%. Strong axis beam to column connections are generally less complex than weak axis beam to column connections. Okay, so we talked about this, several times so far, and you can see the difference between having a column to a connection to the column flange versus a column to the web. And here we're talking about moment connections. So you can see on the right how the plate needs to extend into the web, of course, into the web through the flanges. And look at the shear plate, the shape of the shear plate. It's an extended plate. And of course need to be designed for eccentricity and additional moment for that as well. Okay, run heavy moment connected girders through columns to simplify flow of moment through the columns. So here you can see on the left we have a column that continues through the floor, and look at the connections that are needed. So we have a lot of bolts in the moment connection, a lot of bolts in the shear connection. Instead, we can run the beam through the columns and then have, as you can see, we have at the bottom, we have a cap plate, and then we have bolts connected to the flange of the beam. At the top, we have a base plate with bolts connected with the beam flange. So you can see the reduction in the moment. I'm sorry, the reduction in the moment connection components, like the plates and the welds in a case like that. Run cantilever roof beams over the top of the column. So if it's a cantilever beam at the top where the column doesn't have to continue, this is simple. Just run the column over the cap plate of the column, okay? So you will end up with a simple connection, maybe 4 bolts, like 2 bolts from each side of the web, instead of, as you can see the figure on the right, where we have many bolts needed and heavy moment connection. Minimize the use of little pieces of steel, like brace angles, relieving angles, bent plates, stiffeners, web doubler plates, little beams, okay? Try to minimize these as much as possible, and we talked about several cases where this can be done by increasing, column size, by increasing beam depth, etc. Okay. For example, here, change slab span to reduce the use of small beams. Okay, so in this case here, we can see the direction of the slab, right, is left to right. Okay, if we continue the slab left to right on the cantilever, then we have to show those beams as dashed lines. See, so those short beams as dashed lines. So we have to use those. However, if we just change the orientation of the slab, then we can eliminate those little pieces. Okay, that's what we're talking about when we talk about little pieces. So these are short beams, this could be 4 feet, 4.5 feet, 5 feet, maybe 3 feet or something like that, small pieces. So we can eliminate those by doing that. Avoid skewed beam to column moment connections. This would be really difficult to detail, okay? We have shown moment connections to column flanges and things like that. So we need to avoid something like that. This is really difficult to detail. In a case like this, you could orient the column flanges to take the moment connections, and then, okay, for the beams that are framing into the web, those could be skewed if we have no other option, okay? But the moment connections here would be more expensive and difficult actually to do. Avoid full depth stiffeners where possible, okay? So whenever we have concentrated load on a beam, okay? So of course we have to check, we have to check the beam, whether it needs stiffeners or not. And then we have to design those stiffeners. So avoid extending those all the way to the bottom. The reason for that is when they reach the fillet of the beam, then we need to cut those, and then we need to weld them to the flange. So that's more work. And it can be avoided. Simplify base plates and anchor rod details. Okay, so basically keep the base plates square whenever that is possible. With every footing, we could do that. If we have a base plate that's sitting on top of a wall, then okay, that's a special case and we have to deal with it. It depends on the width of the wall. Okay, but make the base plates square with it whenever that is possible. Hanger connections. So hanger connections could be done in different ways. And depending on how you do it, this may require reinforcing and stiffeners to the web of the beam. Okay, so for example, the figure on the left, okay, we have an HSS member, and that transfers a load through like a cap plate welded to the flange of the column with bolts. So the whole section actually is active in resisting that load. So we would need stiffeners above, okay, to reinforce the web. So this is a bad option. Now, a better solution would be having a gusset plate in the middle, having a gusset plate welded to the bottom flange of the beam, okay, and then have, for example, an angle connected to it. But in this case also, if the web is not good enough to take the load, then we have to provide stiffeners as well. Now, the best option on the right is by having a gusset plate oriented in the same direction of the web in the middle. This way, the load is taken by the web directly, and then have the hanger connection, or the hanger itself, actually, the angle is connected by fewer bolts, as you can see, without any reinforcement. Okay, understand fabricator preferences. Okay, shear connections, moment connections, braced frame connections, truss connections. So if you have these connections on a project or part of them, I have a meeting with the fabricator. Try to understand their preferences for the fabrication, what they prefer for shear connections, what they prefer for moment connections. This will give you an idea, of course, and will allow you to detail your project, properly, without surprises to the fabricator. Avoid torsion and W-shaped beams. Okay, so if we have W-shaped beams, so we may have to do kickers to stabilize those beams. If we're talking about, like, for example, edge beams or spandrel beams in buildings, or beams supporting like facade or brick or anything like that. So open shapes have small capacity in torsion. Okay, small capacity in torsion, and would require kickers or reinforcing or stiffeners. So avoid doing that. You can use HSS members instead in those cases, wherever you have torsion, and closed shapes such as HSS shape have a lot of capacity, or a big capacity for torsion. Okay, camber. Do not camber beams in moment frames and braced frames. Okay, in lateral systems, do not camber. Do not camber short beams. If the beams, or camber, of course, costs money and could be expensive. So do not camber short beams that are less than 25 feet long. Do not camber light beams, like weight-wise, less than 19 pounds per linear foot. So in that case, you can, if you need to camber that, then just increase the size of it, or choose a heavier section and eliminate the camber. Do not over camber, like camber for 75% of steel, of slab plus steel weight. Okay, if you over camber, then of course you may end up still, after the live load and everything, you may still have a camber in the beam. Specify additional concrete to be poured to achieve level floor. So if you, of course, when we design the beams, we have to look at deflections, and of course composite slabs and all that stuff. And this, by the way, happens a lot. So the contractor tries to level the floor, of course, to be ready for the finishes and everything. Now, depending on the deflection they have, they may add concrete that you did not account for in the design. So specify what's required if this has to be done to level the floor, and take that into account in your design. Include ponded concrete load in design. So that's what I just talked about. Do not specify camber less than 3/4 inch. It will not be economical. So if it's less than, if it's say 1/2 inch, just increase the beam by one size, and then you will not need camber at all. Okay, so it will be expensive if the camber is less than 3/4 inch. So looking at this is like looking at what steel shape you need to eliminate camber versus the camber cost. So this is the criteria. So as a tip, do not camber if do not specify camber if it's less than 3/4 inch. Do not specify that camber be measured after that do not specify that camber be measured after erection. If you think you have, do not require that. I think in the design you have to be careful about okay, how much deflection you have, how much camber you need, and how much additional concrete you need to level the floor if that's required. Okay, and of course compare camber cost to material cost. Okay, and that's it. With this, I conclude. I thank you for your for attending. Okay, we have a question here. Can you discuss turn of the nut? Okay, well, there are several methods for closing bolted connections, and the turn of the nut is one of the methods. Of course, we have turn of the nut, we have pre-tensioning, we have twist off, and now turn of the nut. It depends whether we are using this in a snug tight connection or whether we are using this in a pre-tensioned connection. If we are using this in a snug tight connection, this is very simple. We just need to bring the two surfaces together as a snug tight, and that's it. But if it's a pre-tensioned connection, if it's a pre-tensioned connection, then there are requirements in the RCSC, the Research Council on Steel Connections, which you have with the AISC manual. So at the beginning we have the AISC manual. We have the AISC. We have the manual. We have AISC 360. We have the commentary. Just after that, we have the RCSC, the Research Council on Steel Connections. In that, you will see requirements for the turn of the nut pre-tension connection, like how many turns of the nut are needed to achieve pre-tensioning. And of course, it has a discussion about the washers and type of washers and things like that. So I hope that answers your question, but if you need more information about this, you can email me and I can email you the right sections in the RCSC to look at. Other questions? Okay, greater span for concrete deck on formwork may require more expensive form decking for unshored length. So simpler framing could result in more cost elsewhere. Well, it depends how you, I mean, it's a good point, but it depends how you design, okay, whether you design shored or unshored, but keep something in mind that, from like some numbers from the concrete industry about showing that 50% of the cost is from formwork. So formwork is very expensive. And as I said, these numbers are from the concrete industry, where they showed the cost of steel, cost of concrete, and of course the cost of formwork. So you have 20% for concrete, 30% for steel, and 50% for formwork. So this could be very, very expensive. So it depends. It depends, and I think you have. If this is an, if this eliminates maybe fewer beams and then by adding the shoring, you see that more economical. Yes, why not? But in general, this is the case. Other questions? Okay, for composite beam, is it better to show the beams? Is shoring expensive? Yes, shoring is expensive. So, and I have looked at both in terms of like a comparison study in the past. So basically, if you design your composite beams as unshored, you have to design the steel beams as bare steel beams for the concrete, for the fresh concrete load, plus say 20 PSF construction live load. And then, of course, in the second stage, you have to design the composite section for the full load. Okay, so the difference was not much. The difference was not much whether it's short or unshored. So, but shoring is, yes, expensive. Post shoring, can't we just use post shoring? What do you mean? Just posts to support that? That's part of the, yeah, that's part of the, yeah, that's what I mean. I mean, the shoring would be, I mean, regardless, yeah, I think I see what you mean. I think regardless of what shoring type you use, it's still expensive. It's a lot of labor, it's a lot of material. But again, just weigh your options, you know, depending on whether you want to do that or not. And I tell you something, I've seen also a lot of engineers, they design the sections as unshored, okay? And they specify the drawings to be short, which is surprising. I think this is more of just being on the safe side, but that costs a lot of money. And also, you know, it depends on the contractor. The contractor may tell you, no, I want to use shoring, so I want to do it. So so it depends. I suggest discussing that option with with the contractor. It's a very good point. How many post shores per span? That depends, of course, and the shores have to be designed, right? So typically contractors have engineers who design the shoring. Construction engineers typically have experience, on that. So we have to design that. That depends on the thickness of the slab that we're using. It depends on, of course, the size of the beam. So that's the dead load that we have. So the dead load depends on the size of your beams and also on the thickness of the slab, plus the live load, the construction live load that's on the slab. So this need to be designed, and this, by the way, there are several documents on the design of shoring. One of them is from ACI. Other questions? Okay, if there are no questions, I thank you very much for attending and wish you Merry Christmas, Happy Holidays, and Happy New Year. Thank you.